Okay, let's get started. All right, answer to your names, please. Alejo Lagares, Adrian. Alejo Lagares, Justin.
Here.
Dingy. Here. Francois. Bulls.
Here.
Himes.
Here.
Hodges. Oh, oh, yeah, okay. Hodges.
Here.
David.
Here.
Lee.
Here.
Monberg. Martin. Medina. Moreno.
Here.
Oh, Medina is here, actually. And Moreno is here. Perouche. Simmons. Wheeler.
Here.
White. And Zaragoza.
Here.
All right. So, the next topic we're gonna cover, again, as I said before, a lot of what we're gonna cover in this chapter will be a bit of a review. So again, I'm going to go through this rather quickly. So let's talk about Dalton's atomic theory, which was put forward by an Englishman by the name of Dalton. He basically looked at all the information that was known up to that time, and he came up with his theory in 1803 to explain the laws that we were discussing earlier, the law of conservation of mass, the law of definite proportions, and the law of multiple proportions. So based on what he came up with, or based on what he observed, all the laws that we have just discussed, he came up with some assumptions, which collectively is described as his theory, Dalton's atomic theory. And the first one is that matter is composed of atoms that are tiny, indivisible particles. And let me just stick a pin here, because we now know that part of this is not true. Yes, these particles are tiny, but it is not true to say that they are indivisible, because you can actually break down these atoms into yet smaller particles, right? And if you break it down to its most fundamental particles, as we all know, atoms are composed of protons, electrons, and neutrons, right? So this is just one of those things that occurs in science. Somebody comes up with a theory, and then of course, after subsequent discoveries, we know that, okay, at least a part of the theory, if not all of it, is not 100% true, all right? So that's as far as the first postulate is concerned. Now, the second one is that all atoms of a given element are the same. Atoms of one element differ from atoms of other elements, and compounds are formed when the atoms of different elements unite in fixed proportions. And a chemical reaction involves the rearrangement of atoms. No atoms are created, destroyed, or broken apart. All right, so that's basically what Dalton's atomic theory is all about. So just to give a couple of examples, let's say we have a reaction between hydrogen and fluorine. Now, the actual equation for the reaction will be this: H2 plus F2 to give 2HF, right? So basically what this is saying is that for one molecule of hydrogen reacting with one molecule of fluorine, you're going to end up with 2 molecules of hydrogen fluoride. Now, let's say we have a reaction with 3 molecules, or we try to react 3 molecules of fluorine with 2 molecules of hydrogen. Then, of course, based on this equation here, you'd expect that these 2 hydrogen molecules will react with these 2 fluorine molecules, and therefore there'll be 1 fluorine molecule unreacted, all right? So basically, collectively, the number of atoms of each element is the same on both sides, right? Which is basically what Dalton's theory is all about, or what it's saying in part. And as a result, the law of conservation of mass is observed, because if atoms are not created or destroyed in a chemical reaction, then the overall mass total for the products will be equal to the mass of the reactants, right? And that's basically what this is demonstrating, all right? Okay, so that's the Dalton's atomic theory as it supports the conservation of mass law. As I said before, atoms can be broken down into more fundamental particles, where we have the protons and the neutrons residing in the center of the atom, and then dispersed around the nucleus would be the electrons. And this table that you see here is basically a summary of the different particles, their nature, and where they are located in the atom, right? So as far as the proton is concerned, the mass is, relatively speaking, 1 unit, and the charge is +1, and it resides inside the nucleus. The same is true for the neutron. It resides inside the nucleus. Its mass is about the same as the mass of proton, but the difference is that the neutron has no charge. And then as far as the electrons are concerned, the electrons are much lighter compared to either the proton or neutron. In fact, the mass of the electron is about 1/1800 times the mass of either the proton or the neutron. And as stated here, the charge on the electron is -1. And of course, as I said before, the electrons are dispersed around the nucleus on the outside of the nucleus. Okay, so that's basically a summary of the particles and their locations and their relative masses and their charges, all right? Also, another term you should have met before in your Chem 1 experience is this term, isotopes. Isotopes are basically atoms that have the same number of protons, but the number of neutrons are different, all right? And as a result, the masses of these atoms, even though they have the same number of protons, the masses will be different as a result, right? Now, the convention in chemistry and physics normally is that we use the letter Z to represent the atomic number, which of course is the number of protons in the nucleus of an atom. And the mass number is conventionally represented by the letter A, which is the sum of the number of protons and neutrons in the atom, all right? So of course, based on these two numbers, we can easily calculate the number of neutrons. All we have to do is subtract the atomic number from the mass number, and that would give you the number of neutrons for a particular isotope, all right? So this symbolism here that you see here is basically a shorthand way of representing the one particular isotope, right? Where A is the mass number, as I said before, Z is the atomic number, and E is representing the symbol for the element. So for example, there are two major isotopes of chlorine, which are shown here. This one is called chlorine 35, this one is called chlorine 37, right? So basically, because they're isotopes of each other, they have the same atomic number, but of course the mass numbers are different, right? And the mass numbers are different because the number of neutrons are different. So you should be able to answer a question such as this. How many protons are there in chlorine 35? And the answer is 17, right? And then you're asking here, how many protons are present in chlorine 37? And the answer is 17 again. The next question is asking how many neutrons are present in chlorine 37? Nope. Because remember, the mass number is the sum of the number of protons and neutrons. So how will you find the number of neutrons? Exactly, it's a difference between the 37 and the 17, and that will give you the number of neutrons, all right? And if you were to do the same calculation for chlorine 35, you'll see that the number of neutrons is 80. So they're both the same element, but they're isotopes of each other. And they're isotopes of each other because they have different atomic, different mass numbers, or we could say different numbers of neutrons. For that reason, they're isotopes or considered to be isotopes. So again, you should be able to answer a question like this. How many protons, neutrons, and electrons are present in the bromine 81 atom? So how many protons are present in bromine 81? Hint, hint, look at the periodic table, right? You look for which element has the atomic number of what the atomic number of bromine is, and therefore that would be the number of protons. So for the protons, the number would be 35. And for the electrons, it would be 35 as well, because in an atom, the number of protons and electrons are the same. So what would be the number of neutrons? It would be 81 minus 35, whatever that gives, right? So that's what? 646, all right? So the number of neutrons in the case of bromine 81 would be 46. Okay, let's talk about the atomic mass. Now, students always confuse the atomic mass with the mass number. These are two different things, even though they're actually related to each other, but the mass number is different from the atomic mass, right? So just to remind you, the mass number, as we stated earlier, a couple of slides earlier, the mass number is the sum of the number of protons and neutrons in the nucleus of the atom. The atomic mass is something different, right? Now, basically the atomic mass is the mass of the atom expressed in what we call atomic mass units, right? And the definition of the atomic mass unit is shown right here, right? The atomic mass unit is equal to 1/12 exactly the mass of a carbon-12 atom, right? So based on this, we can say that the mass, based on this atomic mass unit scale, the mass of a C12 atom is equal to 12 AMU exactly. All right, based on that definition. So this definition has become necessary because, of course, atoms are very small particles, right? So therefore, using the conventional units like grams and so on would be a bit cumbersome in order to express the mass in those units. But there's a relationship between the gram unit and the atomic mass unit, which is shown right here. One atomic mass unit is equal to 1.66 times 10 to the minus 24 grams. All right, so that gives an idea as to the size of the atomic mass unit. Now, there's a statement here that might seem a bit counterintuitive. It says here that the mass of an atom is not exactly the sum of the masses of protons, neutrons, and electrons, right? That might sound a bit weird because, after all, the atom is composed of protons, neutrons, and electrons, right? And all I'm going to say about that is that there's a reason for that, which I won't get into right now. If you want to know the reason for that, you'd have to wait until we get to General Chemistry 2, where we get to a chapter dealing with nuclear chemistry, or you can research it on your own if you prefer. But basically what you'll find is that there's a difference between the mass of the atom and the sum of the masses of all the particles in the atom. And that difference is called the mass defect, all right? And that's all I'm going to say about that. I won't say anything more because that's a very long and involved discussion. Okay.
Not because they, like a sample of something has like multiple isotopes in it.
No, that's not the reason why.
Okay.
It has to do with as you go from, and I'm delving into Gen Chem 2 stuff. If you were to break up a nucleus of an atom into its particles, right? What you'll find is that energy is required.
Yeah.
Right? And there is a relationship between the energy that is required to break it up and the mass defect. There's an equation. In fact, I'm really jumping the gun here. Delta E is equal to M, delta M times C squared. So delta E would be the energy required for breaking up the nucleus, and delta M would be the mass defect. See what I'm saying? And that's all I'm going to say about that. I don't want to get into anything more deeper than that. You have to wait until Chem 2 in order for us to discuss that, which I'll be teaching next semester. So feel free to enroll in that course. All right. Okay, so let's continue our discussion of atomic mass. So this question you should be able to answer. Do all isotopes of an element have the same mass? And the answer is no, because of course the mass numbers are different, which means that they have different numbers of neutrons, which means that if you compare two or more isotopes, the masses themselves will be different. So you might be wondering, in the periodic table, in most legitimate periodic tables, there are two numbers that are associated with each element, right? One is the atomic number, which we discussed before, right? Which by definition is the number of protons in the atom of the nucleus. So the question is, what is the other number, right? And that other number, we call it the relative atomic mass, all right? In some textbooks, they just simply call it the atomic mass, right? What do we mean by that? Well, you have to take into account, when we get to expressing those numbers, you have to take into account the masses of the different isotopes and their relative abundance, right? Because in nature, most of these elements, they exist as isotopes and exist as relatively fixed proportions of isotopes present throughout nature. So for example, if you were to pick up any compound that contains carbon, And if you can tease out the different isotopes of carbon in that compound, right? Then what you'll find is that the relative amounts of the different carbon isotopes will be relatively constant, all right? And we have to take that into account when we are determining the relative atomic mass, all right? So that's why it states here that the numbers that you see there are what we call the weighted average of the masses of the isotopes that are naturally occurring in that particular element. And to illustrate how those numbers were determined, we're going to look at this example, right? So here we have two isotopes of carbon. There are actually more, but these are the two more abundant isotopes that is present throughout the universe, right? So carbon-12 and carbon-13 are those two isotopes, and these numbers reflect the relative abundance of each of them. So basically, most of the carbon that exists in nature will exist as carbon-12, and a relatively small amount will exist as carbon-13, right? So these are the abundances expressed as percentages, and these are the abundances expressed as fractional values, right? So the question here they're asking, use the data cited above to determine the weighted average atomic mass of carbon. And it gives you that the atomic mass of carbon-12 is this value, and the carbon-13 mass is this value right here. So how do we determine these values? Well, this is the way you go about doing it. What we're going to do is take the percentage, or I should say, take the mass. Let's deal with carbon-12 first, C12, right? We're going to take the mass of carbon-12, which is given as 12.00000 AMU, and we're going to multiply it by the fractional abundance, which is 0.98892. And then we work that out. So let's see what that gives. So that's 12.0000 times 0.99. Oops. 0.98892. And according to my calculation, I got, now this we have to round off to 5 6 feet. So I got 11.867 AMU. And then for carbon-13, we do a similar calculation. The atomic mass for carbon-13 is given here, which is 13.00335 AMU multiplied by the fractional abundance, which is 0.01108. So let's see what that gives. 13.00335 times 0.01108. 0.01108. And according to my calculation, again, no, in this case, I have to round off to 4 6 feet. So that would be 0.1441 AMU. And then what we do next is add these two numbers together, right? And when we do that, we have to round off according to the lowest number of decimal places, which in this case, 3 decimal places would be the extent to which we round off. So 11.867 plus 0.1441. And according to my calculation, this works out to equal to 12.011 AMU. And that would be the relative atomic mass, the weighted average atomic mass of carbon, which is the same as the number that you'll observe in the periodic table associated with carbon, right? And that's basically how all those masses were determined, right? Because not only do you take into account the masses of the different isotopes, you have to take into account the relative abundance, and this is the way you do it, all right? Okay, any questions about this example? Any questions? Any questions? Okay, moving along. So let's talk about the periodic table. And this will be a brief description. We're going to get into it in more detail. But because in a later chapter, we'll talk about why is it that we have the elements in their relative positions. And it largely has to do with the electronic structure of the atoms of the element. All right, so we're going to get into that discussion later on. But for now, just a brief introduction. So this guy, Mendeleev, he was the first person on record to come up with a version of the periodic table, right? So what he noticed was that if you arrange the elements in order of increasing atomic masses, right? Then what you'll find is that after so many elements, their properties repeat themselves, right? Now, back in those days, I don't remember exactly what century it was, but back in those days, the electron, proton, and neutrons were not discovered. So concepts like atomic number wasn't around, right? The only thing that they can go by in those days when it comes to elements would be the atomic masses, and that's what he used, right? So when he made that discovery, he constructed a table where in each column, he put all the elements that has similar properties, right? And what happened was that based on his arrangement, he found out that there were some gaps in his table, which basically represent elements that were not yet discovered, right? And what he was able to do, based on those gaps, he was able to make predictions as to the kind of properties that these undiscovered elements were to display when they're discovered. In fact, I have an example of a comparison between what he predicted for a particular element and what was actually discovered, right? So this is basically an English version of his original table. And where you see the question signs, that's basically like here, there's some missing elements and so on. Anyway, so this is a side-by-side comparison between what his prediction was for a particular element that was called ecosilicon back then, but now we know it as germanium, all right? So this was the prediction in 1871, and this was what was discovered in 1886, right? So he discovered, or he predicted, based on the position of the element in the periodic table, that the atomic mass would be 72. It was discovered to be 72.6. So you can see there's close agreement between what was predicted and what was observed. He predicted that the density of this element would be 5.5. What was observed was a density of 5.47. He predicted that the color would be dirty gray. The color was said to be grayish white. I don't know what the difference is. As far as I'm concerned, they both mean the same thing. He predicted that the density of the oxide would be 4.7 grams per cm cube. It was determined to be 4.703 grams per cm cube. He determined that the boiling point of the chloride would be below 100 degrees. So he was not very specific about that. It was discovered to be 86 degrees. And then finally, he predicted that the density of the chloride would be 1.9 grams per cm cube. And it was discovered that the density of germanium is 1.887 grams per cm cube. So as you can see, there's great agreement between what was predicted and what was observed. And basically, that is all they can do in terms of making predictions based on trends. And as I said before, back then, they didn't know anything about the structure of the atom, which is actually responsible for the trends in the periodic tables in terms of the properties displayed by the elements as you go down a group and across a period, all right? So things were kind of stuck in terms of the knowledge of the relationship between the atomic structure and the position of the elements in the periodic table until the early 1900s, all right? That was when the different particles were discovered, and then people started making the correlation between atomic structure and the position of the elements in the periodic table. Okay, so this is the modern periodic table, of course, without the atomic numbers or the atomic masses. And there are different ways of categorizing the elements based on their positions in the periodic table. Now, one way of categorizing them is according to whether or not the elements are metals, non-metals, or a third minor category known as metalloids, right? So what you'll find is, oh, and by the way, I should mention, most periodic tables, not that one, but this one here, has a line, a thick line of demarcation, as you can see right here, all right, stepwise line, right? That line basically separates to the left the metals and on the right the non-metals, right? And then there are a few elements, as I said before, that are known as metalloids, which are immediately on one side or the other on that same line, right? So as stated here, the vast majority of elements on the left would be metals, with the exception of hydrogen, which is the non-metal, right? And then to the right of the line, that's where we find the non-metals, right? And then you have a minority group of elements known as metalloids, such as silicon, germanium, arsenic, tellurium, astatine. I'm not sure if polonium belongs to that category, but those are basically the metalloids, right? And the metalloids, they are so called because they share some characteristics in common with metals and other characteristics in common with non-metals, right? So if you take, for example, silicon, right? One of the properties of metals is that they are shiny in appearance, right? Copper and so on, they have a shiny look to them. Silicon is also shiny, right? But another thing about silicon is that it's not as good a conductor of electricity as metals, right? So as you can see, silicon has one particular property in common with metals, but not the other, right? So that's just one example, right? And that's basically how metalloids are. All right, continuing our discussion. Now let's talk about molecules and formula. Again, this is something you should be familiar with. Molecules, of course, are basically a collection of atoms held together by covalent bonds. We're going to talk about bonding much later in this course. And then molecular formula, of course, is a representation that gives a number of atoms of each kind present in a molecule. And then there's another term, empirical formula, which gives you the simplest whole number ratio of the atoms present for each element in a compound, all right? Now, what you'll find is that there's a relationship between the empirical formula and the molecular formula. And this is just one example here. So let's say we're dealing with hydrogen peroxide and the molecular formula is H2O2, right? So what this tells you is that for every molecule of this compound, there are 2 atoms of hydrogen and 2 atoms of oxygen, right? The empirical formula gives you the simplest ratio between the hydrogen and oxygen. So therefore, this is the molecular formula and this is the empirical formula, because the empirical formula basically tells you that there's a 1-to-1 ratio between the hydrogen and oxygen, all right? So with that said, let's look at octane. This is the molecular formula for this compound known as octane. So what do you think the empirical formula of octane is? Remember, the empirical formula gives you the simplest ratio of, in this case, between the carbon and hydrogen. C4H9 would be indeed correct, right? So here, right, so that would be the empirical formula of octane. So what this is telling you is that there's a 4-to-9 ratio between the carbon atoms and the hydrogen atoms in octane. Okay, there's some other representations of compounds that are oftentimes useful. Structural formulas, basically structural formulas of, and this is particularly true for molecular compounds, not ionic compounds. They basically show you how the atoms are connected to each other. And there are some variations of structural formulas. Now, this here is the structural formula, and more specifically, the condensed structural formula for a compound known as acetic acid. So the way you interpret this is that this carbon here is simultaneously bonded to 3 hydrogen. It's also bonded to this carbon. This carbon is bonded to these 2 oxygens, and this oxygen is bonded to the hydrogen, right? Now, what you can use in order to show a more clear picture in terms of how the atoms are connected, you can use some other forms of structural formula. Let me see if I can squeeze it in here, which looks like this. CH3, then you have a bond, then C double bond O, and then OH. Now this one is more clear compared to what I just discussed here, because it shows you explicitly how the atoms are connected, right? And yet we can use this representation here, the ball and stick model, right? This is very important, especially for those of you who have to do organic chemistry, right? This is very important because not only does it show how the atoms are connected to each other, but it gives you a 3-dimensional picture, right? Which is very important for a lot of organic reactions, right? In order for you to understand some organic reactions, you have to basically understand what the 3-dimensional structure is so that you can make predictions of, let's say, what kind of product you're going to expect to get when certain reagents react with a particular molecule, all right? So, the typical convention when it comes to the use of ball and stick models is that the black spheres usually represent carbons and the white spheres usually represent hydrogens. And then as far as oxygen is concerned, they use red here, but you can use some other colors, doesn't matter, and other colors for other atoms, all right? So that's basically the ball and stick model. And then this one is called a space filling model. Now, to be perfectly honest, you don't have to use this. I don't think you'll be using this in organic chemistry, but in more high-level research, like medicinal chemistry or pharmaceutical chemistry, this is very important, all right? Because when it comes to investigating how drugs interact with biological systems, you have to not only take into account how the atoms are connected to each other, but the amount of space each atom takes up, right? That's very important because in a lot of drug interactions with biological systems, you need to have the molecule to be able to fit into what is called an active site, which will trigger whatever effects, hopefully beneficial effects of that drug, right? So, you know, chemists really work hard at basically structuring molecules with the right atoms so that the amount of space occupied is just right so that you have that fit into the active site so that the therapeutic effects of drugs can be witnessed, all right? So for those of you, if you plan to do, you know, high-level research, you know, in biochemistry, chemistry, pharmaceutical chemistry, then you'll find that this is very often used to represent, or this type of modeling is used to represent, especially biomolecules, proteins, drugs, and so on. Okay, just skip all this here. Okay, so now we're going to get into nomenclature. Of course, nomenclature is that area of chemistry where we're dealing with how do we name compounds, and there are certain rules that we have to obey when it comes to naming compounds. There's an international organization known as IUPAC. IUPAC. It stands for International Union of Pure and Applied Chemists, right? And there's a division within this group that meets ever so often. I think they meet every 4 years or something like that. And their sole purpose is to basically come up with new rules for naming compounds, right? And the reason why they have to meet ever so often is because every year new compounds are being made, and therefore, even though you might have established rules before, what happens often is that the new compounds are such that it's necessary to either change rules or come up with rules to accommodate those new compounds, right? So the rules that we're going to cover is the rules that was devised by the division within this organization, right? Okay, so basically, before they used to have common names, different compounds. The problem with common names, of course, is that they describe more often than not the properties of the particular compound, but doesn't give you any information about the composition, right? So that's the main reason why we have what is called a systematic method for naming compounds and also writing the formulas based on their names, all right? So what we're going to look at is looking at how do we name what we call binary molecular compounds, right? Binary molecular compounds are basically compounds made up of two elements that are nonmetals, all right? So how do we name these compounds, right? So the first thing we need to recognize is that the name consists of two words, because after all, there are two elements in the compound. The first word would be then the exact name of the element as it appears first in the formula, all right? The next word, right, starts off with the stem of the name of the second element, but ends with IDE. So for the second element, the ending is always IDE in terms of the ending, right? And then after that, their names are modified by adding prefixes to indicate the number of atoms of each element in the molecule. And let me just hasten to say that there are two exceptions to this particular rule, all right? And we're going to get into those exceptions shortly. Now, going back to what was said, let me go back here. Going back to what was said here about the first word and the name of that element. Oftentimes you have to figure out, okay, what would be the first element in the formula or the first word in the name. Now, you could memorize this chart, which I would recommend, but the general rule of thumb is that the less electronegative element is the one that is named first, right? Or if you want to look at it in terms of the relative position to the periodic table, the element that is further down and to the left of the periodic table is the one that's named first. I prefer to just say the less electronegative element, all right? And of course, I provided the table in Canvas for you guys to refer to. I think the last page gives you the electronegativities of the different elements. So you can use that to help make a prediction as to which element will be indicated first in the name. So for example, if you have a binary compound made up of arsenic and sulfur, based on what I just said, which element would be named first? Remember I said the less electronegative element, or the element is further down and to the left of the periodic table. So which one of these two, arsenic or sulfur, is further down or to the left and or to the left of the periodic table?
Arsenic.
Arsenic, exactly. So arsenic would be named first and then the sulfur would be named after that, all right? Okay, so just to give you a couple of examples, well, more than a couple, of the use of prefixes along with how it applies to naming binary molecular compounds. Okay, so in the case of the first one here, and this is where the exception comes in that I mentioned earlier, right? The prefix mono means one, of course, right? Now look at the name of this molecule. It's called nitrogen monoxide. Now you might be wondering, okay, since we have one nitrogen, why don't we call it mononitrogen monoxide? And the answer is, and I probably should write this down. So this is an exception, right? And the exception is this. If the first element in the formula has only one atom, then no prefixes are used. All right. So in this case here, if you look at the formula for NO, there's only one nitrogen atom, the first element, right? Only one nitrogen atom, right? So therefore, we do not use any prefixes, no mono for the nitrogen in that case. And in fact, also in the case of NO2, again, for the same reason, there's no mono in front of the nitrogen. So therefore, in the case of NO2, the name is simply nitrogen dioxide. All right. Now, in the case of the third example, right, you'll notice that you have a prefix of, I'm sorry, not prefix, a subscript of 2 for the nitrogen and 3 for the oxygen, right? So for that reason, the name of this compound is dinitrogen trioxide, right? Di for the 2 nitrogens, tri for the 3 oxygens, right? If you look at this one, the name of this compound is dinitrogen tetroxide. And let me just say, in this case here, I've seen this in textbooks, which means that according to IUPAC, this is okay. You could also call this tetraoxide. Tetraoxide. So tetraoxide and tetroxide, as far as IUPAC is concerned, they're both acceptable. All right. Here's another one. Dinitrogen pentoxide. Again, you can use pentaoxide as well. Oxide as well in that case, right? So basically, you need to remember these prefixes, by the way, right? And for at our level, we go up to 10, right? You can actually go beyond that, but at this stage, we'll just go up to prefixes representing up to 10 atoms, right? Here's another example. SF6. Now, in this case, there's only one sulfur atom, so we do not use mono, right? And we have 6 fluorine atoms. So the name of this molecule is sulfur hexafluoride. In this case, IF7, iodine heptafluoride. And then in this case, P4808, that's tetraphosphorus octoxide or octoxide. And then we have P4S9, tetraphosphorus monosulfide, and then AS4O10, tetraarsenic decoxide. So these are basically just some examples of naming molecules based on their composition and taking into account the number of atoms of each element present, and that's accounted for by use of prefixes. While I'm at this page, let me just mention another exception when it comes to naming binary molecular compounds. And we're going to see some examples of that later on when it comes to acids. So here's another exception. If, what should I word this? If in a binary molecular compound, one of the atoms is hydrogen, then no prefixes are used for either atom. No prefixes are used for either atom. All right. So if you're dealing with a binary molecular compound, which of course have two elements, one of which is hydrogen, then you do not use prefixes for hydrogen or the other element, right? And let's see something here. So I'm just going to do a quick example. So let's say, for example, you have let's squeeze it in here, HCl, right? This, the name of this compound would simply be hydrogen chloride. Chloride, all right? So it would be improper for you to call it monohydrogen monochloride, right? It's just simply hydrogen chloride. Here's another example, H2S. This is simply hydrogen sulfide. Hydrogen sulfide, all right? So in those cases, as you can see, again, no prefixes are used, right? So if one of the elements is hydrogen, doesn't matter what the other element is, as long as it's a binary molecular compound, then no prefixes are used for either element, all right? So that's basically another exception that you need to keep in mind. We're going to see some examples of this later on when it comes to naming acids. But before we do that, let's look at these two examples. The first one which says, write the molecular formula and name of a compound for which each molecule contains 6 oxygen atoms and phosphorus atoms. Now, if you're going to write the formula or the name, the first question you have to ask yourself is, which element comes first? So let's deal with the formula, right? Which element will be indicated first in the formula when you're combining phosphorus and oxygen?
Phosphorus.
Exactly. Remember, it's the less electronegative element, or the element that is lower and to the left in the periodic table. So if you look at the relative positions of oxygen and phosphorus, phosphorus is in the row below and to the left of oxygen, right? So basically, because this molecule, according to the question, contains 4 phosphorus atoms, you're going to start off with P4 and then 6 oxygen atoms, which will be O6, right? So that's the formula. So now we have to ask ourselves, what's the name of this compound? So what do you think the name of this compound is? Remember now, you have to take into account the prefixes, and also you have to remember that the second element always ends with IDE in terms of the name, right? So based on that, what do you say the name of this compound is? Tetraphosphorus spelling's right. Okay, tetraphosphorus hexoxide, or you can say hexa oxide as well. Both are allowable under IUPAC rules, all right? Okay, so that was the first one. The second one is asking for you to write the molecular formula of phosphorus pentachloride. So what say you is the answer for A?
Uh,
Cl5, exactly, okay. And then in the case of B, they're giving you the formula and asking for the name, so what say you is the answer for B? I'm sorry,
Diesel. So. Diesel.
disulfur,
That's the fluoride.
pentafluoride, disulfur. No, not penta, sorry,
That's the fluoride.
decafluoride. Decafluoride. All right. Okay, very good. Okay, any questions about any of these? Any questions? Any questions? Okay, moving along. Okay, so now we have just discussed how to name binary molecular compounds. Now we're going to talk about naming ionic compounds. All right. Now, of course, we need to remind ourselves as to what ions are. And what you'll find is that ions are basically atoms or group of atoms that either gains or loses electrons, and that unit carries a charge. All right. Now, please note that when it comes to the monatomic ions, meaning ions that are formed from an atom, there's no change, I should say, in the number of protons or neutrons in the nucleus. The only change will be is in the number of electrons that it has. So therefore, if you have a monatomic, if you have an atom, I should say, that loses electrons, then the resulting ion will be positive, and it's called a cation. And then an anion is what happens when an atom gains electrons, right? So the cations are positively charged and the anions are negatively charged. Now when you have ions coming together, and I should add ions of opposite charges coming together to form a compound, that compound will be neutral as a result of the total number of plus charges cancelling out the total number of negative charges. So one example of this is sodium chloride, right? Sodium chloride is made up of sodium and chloride ions. The sodium ions have a +1 charge, the chloride ions have a -1 charge, right? So therefore, basically in any sample of sodium chloride, the number of sodium ions and the number of chloride ions will be the same, right? Because the charges will cancel out, right? One thing you need to remember, when it comes to binary ionic compounds, one big difference between them and molecular compounds is that there are no discrete units of the compounds present. So for example, in the case of sodium chloride, there's no such thing as a molecule of sodium chloride, right? So you can have a molecule of, let's say, sulfur dioxide or carbon dioxide, and so on. But when it comes to ionic compounds, you don't have any discrete units. What you have is something looking like what you see here on the screen, right? You have basically a very regular arrangement of the ions according to a certain pattern, right? And basically what you can find is that it's very regular, which means that you can identify what is called a unit cell, which has a particular arrangement, and that arrangement is repeated throughout the growth structure of the compound, right? So this is what sodium chloride looks like, at least a portion of it, because of course it extends to many other ions being involved, all right? So that's basically true for not only sodium chloride, but true for pretty much all ionic compounds. They may differ from one to the other in terms of how the ions are arranged, but they all have the same situation where you can identify a unit cell, and that cell is repeated throughout the whole structure, all right? So that's one big difference between binary ionic compounds and molecular compounds, all right? So the monatomic ions, as I said before, are ions that are formed from an atom, either as a result of the loss or gain of electrons. And there are certain patterns that will emerge based on the position of the different atoms in the periodic table. So for example, those metals in group 1A, they will lose 1 electron to form an ion with a +1 charge. Elements in group 2A would lose 2 electrons to form an ion with a +2 charge. And in the case of aluminum, which is in group 3A, those atoms will form ions with +3. Now things become a bit more complicated for those elements apart from aluminum in group 3. All right, but aluminum itself will form an ion with a +3 charge as a result of losing 3 electrons. And then when you get to the other side of the periodic table, with respect to elements in groups 5, 6, and 7, what you'll find is that they tend to gain electrons to form charges -3, -2, and -1 respectively. And all of this that we observe is based on the electronic structure. And as I said before, later on in this course, we're gonna learn about how the atomic structure relates to the formation of ions of particular charges. Things become a bit more unclear or less predictable, I should say, when it comes to what we call the transition elements. The transition elements are basically the elements which occupy the region. Well, let me go back to the periodic table that I had before for the sake of those folks joining us by Zoom. Okay, so the transition elements are basically the elements in this region right here, right? In addition to these elements right here, right? And what you'll find is that in terms of predicting the charges that these ions would carry, that's more difficult. Things are not as predictable as in the case of the non-transition elements, right? And in fact, there are some instances where you can have one particular metallic atom that can form ions of different charges, right? That even adds more complexity in terms of making predictions, in terms of what type of charges monatomic ions can carry, all right? So as stated here, oftentimes elements in these regions can form ions of more than one charge. And in order to make distinction between these ions, we use Roman numerals to basically indicate the charge carried by elements in this region, right? So for example, there are two types of copper ions. One would be copper with a 2+ charge, and the other would be copper with a +1 charge. This one is called copper 2. And this one is called copper 1. So in order to indicate the name or to make a distinction in terms of the name of these ions, even though they're from the same element, but by virtue of the fact that they have different charges, you have to indicate that in their name and also in the compounds that contain these ions, all right? Okay, now there are some transition elements such as silver and zinc and cadmium. They are within the transition elements, but they only carry one charge, right? And therefore, you don't need to indicate the charge in the name using Roman numerals. In fact, according to IUPAC, if you have a metal element that only form ions of a particular charge, then you should not use Roman numerals, right? So elements like magnesium, calcium, sodium, potassium, which only display a particular charge, according to IUPAC, do not use Roman numerals associated with these ions, because according to those guys, that is being, you're going overboard, or what's the word I'm looking for? It's not necessary, all right? But for those that display more than one charge, then you have to indicate the charge using Roman numerals. Okay, so with that said, let's see if we can answer these examples. Determine the formula for calcium chloride. Now, in order for you to determine the formula for calcium chloride or for any ionic compound, you'll find it helpful to use that table that is provided in Canvas, right? Which again, as I said before, you'll have access to that table during your exams, right? Because there are 3 pages in that document which has the list of common ions, right? So if you consult that table, you'll see that for calcium, the charge carried by the calcium ion is +2 or 2+, right? And then for chloride, the charge carried by the chloride ion is -1. Now remember, the entire compound must be neutral. In other words, the total number of plus charges must be equal to the total number of negative charges. So to achieve that, what we have to do is multiply this by 2, right? And then when you put this together, the answer becomes, right? So this 2 here becomes the subscript in the formula. And please note, in the formula, there's no charges indicated because the charges will cancel out each other, all right? And that's basically how you do A. So how will you do B? Magnesium oxide. How will you determine the formula for that compound? What's the charge on the magnesium ion? 2 plus. And what's the charge on the oxide ion? -2, right? So therefore, you don't have to multiply any of them by anything, you just put them together because the charge is already equal, but opposite, all right? Okay, what about the next example, A? Now this time you're doing the reverse. They gave you the formula for the compounds, and they're asking for the names, right? So what would be the name of this compound here? Magnesium sulfide. All right, and what's the name of the other one? Now, the other one you have to be careful, because chromium, it turns out, can form 2 types of ions, I should say. One with a +2 charge and one with a +3 charge. And if you look at your table, you see that's the case, right? So remember now, we need to indicate the charge using Roman numerals. So the question you have to ask yourself is, what is the charge carried by the chromium in the case of B? +3, right? So what would be the name of this compound? Chromium 3 chloride. That's it. All right, so you have to be careful, right? When it comes to, the transition elements that can display more than one charge, right? You have to figure out what the charge is first, and then you include that in the name of the ion and also the name of the compound. All right, any questions about this? Any questions? Any questions? Questions? Okay. Okay, so let's see here. So this is just basically summarizing the monatomic ions and where they're located in the periodic table. As I said before, there are some elements that can display more than one charges in their ions, such as chromium, manganese, iron, and of course you have to use Roman numerals. Lead is a bit of an outlier because lead is not a transition element, but lead can also exist as, well, not only lead, but tin as well. Lead and tin can exist as +4 in addition to +2. So let me just put that here and here. So these are kind of unique in terms of the charges that they can display, because they can display more than one charge, but they do not belong in the transition region. All right. Oh, this is just asking what's the charge on the zirconium ion? And the answer is +4, because you have 4 expressed as Roman numerals within parentheses in that formula. Okay, so this is just summarizing what we were talking about in terms of naming binary ionic compounds. Again, let me remind you, there are no discrete units of ionic compounds. So the formula that we were looking at is not, you would not call them molecular formulas, right? In fact, they will be empirical formulas because they give you the simplest ratio of the different elements present in the formula, right? I'm not going to go into all this because basically we just covered this in terms of looking at the examples that we looked at earlier. So let me remind you that when it comes to binary ionic compounds, their names always ends with IDE. So that's one thing in common with binary ionic compounds and binary molecular compounds. The last element or the second element ends with IDE along with the stem of that name of that element. Okay, now we get to another type of ions known as polyatomic ions. And as the name suggests, these are ions which are made up of a collection of atoms held together by covalent bonds, but that collection of atoms as a unit carries a charge, right? And the table I provided also gives you a list of those ions. And as stated here, there are many more polyatomic anions compared to polyatomic cations. In fact, they're only at this level 2 types of polyatomic cations. One is the ammonium ion, and the other one is the mercury 1 ion. And I think there's another one which I can't recall right now. Now, you can ignore this line right here. I don't expect you guys to memorize all these ions, even though what you'll find is that when you work with these ions repeatedly, you find yourself knowing them. But I'm not going to ask you to sit down and memorize all these because, my philosophy is that it's more important that you know how to, use the information or use it or apply concept than to just arbitrarily memorize different facts, all right? Some of the names of these polyatomic ions will contain hypo and per as prefixes, which basically indicates, not directly, but relatively speaking, how many atoms of oxygen are present in those polyatomic ions. And those ions are known as oxo anions because they contain oxygen, right? And then you'll find that some of these polyatomic ions will end with ITE or ATE ending, again, depending on the amount of oxygens that are present, all right? Okay, and this is just a small list of different polyatomic ions. As I said before, the table that I provided in Canvas is more comprehensive, right? So that's what you'll be using to answer questions, right? Okay, so let's see how we apply what we have just learned to the naming of these compounds, right? So in the case of A, they're asking for you to write down the formula for sodium sulfate, right? So in the case of sodium sulfate, you have access to the tables. You can look up the formula for sodium. Formula for the sodium ion is Na plus, and the formula for the sulfate ion, is SO3 2 minus, right? So again, as in the case of binary ionic compounds, we have to ensure that the total number of plus charges are equal to the total number of negative charges, which means that we have to multiply this by 2. So when we put this together, this becomes Na2SO3. And that would be the answer for A, all right? Now, in the case of B, right, ammonium sulfate, so if you consult the table, you'll see that ammonium has this formula, and the sulfate ion has this formula, right? Now, in this case, again, you have to ensure that the number of plus charges are equal to the number of negative charges, so that means you have to multiply this by 2. However, when you put these together now, you have to be careful, because you should recognize that sodium is a polyatomic ion, right? So how do we deal with this in terms of putting the formula together? In the case of polyatomic ions being present in the formula, what you need to do is surround it with parentheses, and then you put the number here, down here as a subscript, right? And then you write down the rest of it, which is the SO4, right? So remember, when you're dealing with polyatomic ions, if you're indicating more than one of them, right, then you need to put it within parentheses and then put the actual number outside as a subscript in the formula, all right? Oh, and I made a mistake here. Let me take care of that now. The plus sign should not be there, so let me take it off. There should be no signs indicated in the final answer. All right. What about the next example? It's asking for the name, and they gave the formulas for these two compounds. So for A, what's the name of this compound? Anybody? What's the name of NaCN?
Carbon.
Well, you're right for the first part, sodium, but there's a name given to this ion right here. Yeah, you may want to consult your list of ions in order to answer this.
Cyanide.
That's it. Something you don't want to drink unless you're contemplating suicide. All right? Okay, what do you think the name of the other compound is? B, MgClO4 2. Well,
Magnesium.
Magnesium,
Perchlorate.
perchlorate, is that? Okay, very good, all right. Let's continue. Okay, now there's a special group of compounds that we may not be familiar with, but. Well, I don't cover it in my introductory chemistry class, so. Known as hydrates. The thing about hydrates is that there is an ionic part of it, so you're going to have, like, just as how you have ionic compounds, you're going to have that part to that compound. But also as a part of the whole structure of the compound, you're going to have a fixed proportion of water molecules present per formula unit, all right? And basically, when it comes to naming these compounds, you'd have to name the ionic part just as you would have in the case of ionic compounds. But you also have to include in the name the number of water molecules present per formula units, right? So the way we indicate that is that we use a prefix followed by hydrate. So you can have monohydrate, dihydrate, trihydrate, and so on. So just to give you, and before we get to the actual example, in terms of the formula, what we do in terms of representing the formula for the compound is that we write down the ionic part, then we put a dot, and then we put the number of water molecules, right? And I think I have one example here, right? For example, in this case here, BaCl2 dot 2H2O, right? So what this is saying is that for every formula unit of barium chloride, you have 2 water molecules present, all right? So the name of this compound is barium chloride dihydrate, right? This is the barium chloride part, and because you have 2 water molecules, it's called a dihydrate. In the case of CuSO4 dot 5H2O, the name of this compound is copper 2 sulfate pentahydrate. All right. Again, the copper 2 sulfate is the ionic part, and then the pentahydrate takes care of the 5 water molecules per formula unit of copper 2 sulfate. All right. So a couple of things I want to mention concerning hydrates. One important property that all hydrates have is that you can easily remove the water from the hydrate. So for example, in the case of barium chloride dihydrate, and by the way, let me say this also, probably should have mentioned it on the previous slide. There's no way that you can directly predict the number of water molecules. The only way you can determine the number of water molecules is by experiment, right? Now, this is the formula for barium chloride dihydrate, and you can easily remove the water by simply heating it to 100 degrees Celsius. And you're going to end up with BaCl2 plus 2H2O, right? So this is called the hydrate. And when you heat it to remove the water, what is left is called the anhydrous salt. Or in some textbooks, they call it the anhydrate. So any one of those two terms can be used, all right? So, and that is true for all hydrates, right? Basically, if you start off with your hydrate, you heat it to 100 degrees and you heat it long enough, some will take more heat than others, but eventually all the water will be driven off and you'll be left with the anhydrous form. And what you'll find is that there is a change in the appearance of the substance as you remove the water. What you'll find is that in the case of the barium chloride dihydrate, the color for both the anhydrous and the hydrated form would be white, right? But the difference would be that this would have a more crystalline appearance, right? While this would have a more powdery appearance. So even though there's no color change, right? There's still some change in the appearance, whereas the hydrate form would be more crystalline. You see some crystals, some shiny crystals of the barium chloride dihydrate present. And then after heating it, it has a more amorphous, powdery appearance, right? Now, there are some instances where there's a color change that will be observed. And that is true in the case of copper 2 sulfate, which is demonstrated right here. So in the case of copper 2 sulfate pentahydrate, this is the equation for what happens when you heat it, right? So this is the hydrate. And when you heat it to 100 degrees Celsius, you're going to get CuSO4 plus 5H2O. Now, in this case, there will be an observable color change in that the copper 2 sulfate hydrate, pentahydrate, would be blue in color, while the copper 2 sulfate anhydrous would be white, right? So in some instances, you're going to see a color change, and that is what is being demonstrated here. This is the blue colored copper 2 sulfate, and when you heat it and drive the water off, then you're going to end up with your white copper 2 sulfate anhydrous form. Another thing I should mention is that this reaction is easily reversible, right? So if you add water to your anhydrous copper 2 sulfate, you're going to get back the blue colored hydrate, and that is what is being shown here. Somebody is adding water to the anhydrous copper 2 sulfate, and you notice that where the water is added, it becomes blue, right? So you can go back and forth in terms of removing water and adding water, and you're going to see the corresponding color change. What time is it? Okay, about 5 more minutes. All right. So that's basically how hydrates work. And for those of you who are enrolled in my lab, is that all of you? You'll be doing one experiment involving hydrates where you'll each be given an unknown hydrate. And based on driving the water off and determining the percentage of water present in the hydrate, you can identify what your unknown is. So that's basically what you'll be doing in that experiment. Something for you to look forward to. Okay, you know what? I'm going to stop here. I don't want to start this and then stop in the middle of it. So we're going to call it today. But let me just say this. In the meantime, what I would suggest you do, I'm going to publish assignment number 2. If I'm not done so already. Let me check and make sure. Oh, shoot. Oh. Looks like I didn't even publish the folder. Okay, so let me do that now. And then let me publish assignment number 2. And you guys can get started on that assignment. Let me just check something here. Let me see how far you can get into assignment number 2 based on what we have done so far. Okay, you certainly can do number 1, number 2, number 3. Let me just say this, number 3 is a bit of a challenge, right? So I'll follow that. Let me see here, number 4, number 5, number 6, number 7, number 8, number 9, number 10, number 11, 12. Okay, you cannot do number 13 anymore. Okay, so just attempt all questions up to number, let's say number 30. Up to number 12. So you can't do number 13, right? So try those. If you have any issues, problems with those, you can, contact me during office hours. And I'm more than willing to help, right? All right, so that's it, folks. I'll see you guys on Tuesday. All right, here. Oh, who came in late? Hold on. Sorry. Let me see here. Alejo, Lagaret, Adrian.
Here.
Francois. Momberg. Momberg, Martin. Perouche. Simmons. White. Yes, sir.
If I just have a couple questions.
Yes, sir.
Interface in the picture. Around, or not this one.
This unit here.
And now, no longer.
Okay. If I remember correctly, when I did this, I started off with 1 meter cube, and then I multiply by this relationship here, which is 1 meter cube down here and 1,000 liters above. And then I multiply by 1 liter below and 1,000 cube. But that's it. This goes with that. So the answer is 10 to the 6.
So, oh, okay, so we,
So the only thing that's right, the only thing that's missing here is that you should have started off with 1 meter cube.
1 meter. cube.
Because the question is asking how many milliliters are in a cubic meter. So you're gonna start with 1 meter cube, which is what I did here, and then I just do the rest.
Yeah, I skipped that part because I knew like 1,000.
Right, hold on 1 minute. You guys out there in Zoom, I'll be signing off now.